Welcome to the Daily Tech Feed, Hacker News. I'm Jack, and it is March 18th, 2026. Today's feed is genuinely good. Rob Pike's 5 Rules of Programming, Making Timeless and Still Ignored. A deep dive into JPEG compression that actually makes you appreciate the math. Someone built a CPU from scratch and wrote it all up, which is exactly the kind of thing that makes me love this community. There's Nightingale, open source karaoke for any song on your machine. And Mistral Forge. Let's get into it. There's a small irony buried in the comments on this page, and it illuminates everything. The article attributes premature optimization is the root of all evil to Tony Hoare. Multiple commenters flag this. It's actually from Donna Knuth's 1974 paper, Structured Programming with Go-To Statements. Knuth credited Hoare with a related but different idea. The misattribution has been circulating for decades. Rob Pike's Rules 1 and 2 are literally about not guessing where your problems are. And here we have a 50-year-old guess about who said that, still circulating. That's not a gotcha. That's the rules working in reverse, showing you exactly why they exist. Pike wrote these at Bell Labs, probably in the 1980s, during the period when Unix was being built and refined. Ken Thompson, his colleague, co-author of Go, co-creator of Unix, took Rules 3 and 4 and compressed them further. When in doubt, use brute force. The lineage matters. These aren't abstract principles from a theorist. They came from people who built systems that are still running today. Now, apply the engineering lens. Rules 1 and 2 are about measurement as epistemic discipline. You do not know where your program spends its time. The profiler knows. This is not humility for its own sake. It's precision. An optimized system built on a wrong assumption about the bottleneck is a closed system. It has bet on one future and made that bet hard to reverse. Rules 3 and 4 go deeper. Fancy algorithms have big constants and big bug surfaces. A binary search tree with 20 elements is not faster than a linear scan. It's just more code to maintain and more ways for something to fail. Simple algorithms keep the system legible. Legibility is leverage. Rule 5 is the one that doesn't get enough credit outside the Unix tradition. Data dominates. Get the data structure right and the algorithm becomes obvious. Sometimes trivially obvious. The inverse is also true. Wrong data structure and you're fighting entropy forever, adding clever code to compensate for a foundational mismatch. Fred Brooks said something similar in The Mythical Man Month in 1975. The lineage runs from Brooks through Pike, through Thompson, Bell Labs to Go. And the idea hasn't changed. Show me your data structures, and I'll tell you whether your system has a future. Simple things that you can reason about. That's the craft. Now, story 2. Pause the hidden math inside every photo you've ever sent. Every JPEG you've ever seen is a compression of human perception, not just of data. Here's the craft underneath it. When you encode an image as a JPEG, the algorithm doesn't work on pixels directly. It slices the image into 8 by 8 blocks, then runs each block through a discrete cosine transform. The DCT converts those 64 spatial values, row brightness at each pixel, into 64 frequency coefficients. Low frequencies capture broad shapes and gradients. High frequencies capture fine detail, sharp edges, texture. The elegant part. Human vision is terrible at high-frequency detail. Not terrible in the pejorative sense. Terrible in the precise engineering sense. Our eyes evolved to detect motion, faces, contrast at scale. We genuinely cannot perceive most of the high-frequency information in a natural image. So JPEG quantizes aggressively there, discards most of it, keeps the low-frequency coefficients that our visual system actually uses. This is the insight that made it work. The compression isn't destroying information at random. It's destroying the information you were never going to see anyway. It's lossy in a way that's tuned to the specific receiver. That receiver is you, the artifacts people call blocky. The quality degradation you see in heavily compressed images. That's the pay-by-gate DCT grid becoming visible. You're watching the algorithm's seams. At normal compression, those seams disappear into the continuous signal your brain constructs. Push the quantization too hard, and the seams win. The craft is in calibrating exactly where that threshold sits. One commenter put it cleanly: JPEG does what MP3 does. Both formats filter for human perception. Audio compression attacks frequencies our ears can't localize. Image compression attacks spatial frequencies our eyes don't resolve. Both algorithms start with a model of the receiver, not just the signal. That's the level of thinking that makes them last. Sophie Wang's piece walks through the whole mechanism with interactive visualizations. DCT coefficients, quantization tables, the reconstruction process, the kind of explainer that takes something most engineers treat as a black box and makes it legible. The format is 30 years old and still running on billions of devices. You don't achieve that with clever hacks. You achieve it by solving the actual problem, which turned out to be a problem of human biology as much as information theory. The tools exist. The knowledge is available. Someone just took the time to write it down clearly. Next up, a builder takes us inside their homebrew CPU. Full custom silicon from scratch. The case against building your own CPU from discrete logic is genuinely strong. Your time has value. The design was already validated in simulation. You can buy a microcontroller for less than a cup of coffee that outperforms anything you'll assemble on a breadboard. Every hour spent chasing a floating address line is an hour you could have spent shipping something. By any reasonable cost-benefit analysis, the exercise is unnecessary. That argument is correct on every point, and it misses the entire thing. Consider how civil engineers work. Finite element analysis can model how a bridge will behave under load with remarkable fidelity. Material properties, thermal expansion, dynamic loading, resonance frequencies. The software is extraordinarily good. And then they build the bridge anyway because the model is a theory and the structure is an argument with physics. And those are not the same thing. The concrete has tolerances. The steel has grain. Reality introduces variables. No simulator was built to carry. Will Warren validated WCPU1 in Logis. It worked. He was confident. Then he started wiring the physical hardware, and the education began in earnest. Backwards LEDs. Floating address lines on EEPROMs that behaved as cursed. The discovery learned the hard way that ordering SMT parts for a prototype when you will end up on breadboards anyway is an expensive lesson about package formats. He learned to read binary by staring at blinking lights because he hadn't built an output register yet. Each failure is precise information about the gap between the map and the territory. You cannot purchase that information. You cannot simulate your way to it. He designed an EVM programmer board, used Claude Code to implement the serial protocol, iterated on microcode. He found a timing constraint the hard way. Control pins routed through shift registers limiting write speed, forcing 1 byte at a time, writes at 80 seconds per chip, instead of page writes at 1.3 seconds. He knows why now. He knows it in his hands, not just in his head. Reader responses to the post are dense with specific actionable improvements. Parallel 590As instead of a 377, behind a 245 tape-out suggestions. That's what happens when you build something real and publish it. The knowledge compounds outward. The simulation proved the design. The breadboard proved the engineer. Next up, open source karaoke. Because sometimes you need to sing along to literally anything in your music library. What does it mean for a technology to be genuinely available, not gated behind a paywall or an enterprise contract, but actually in your hands doing real work on hardware you own? Nightingale is a karaoke app, open source, local. You point it at your music folder and it runs. Stem separation via UVR karaoke model or DMUX. Word-level lyric alignment via Whisper X. Real-time pitch scoring. Multiple player profiles. Gamepad navigation. GPU shader backgrounds. Drop in a video file and the original footage becomes your backdrop while you sing. The whole thing working together offline. Now here's where I want to play devil's advocate, because there's an argument worth taking seriously, that applying these tools to karaoke is somehow beneath them, that UVR and DMUX were built for music production, that WhisperX was built for transcription, that pitch detection belongs in professional audio software, that this is a toy use of serious technology. Run that argument forward and it collapses almost immediately, because the measure of whether open tools have actually landed, whether they've escaped the lab and entered the world, is exactly this moment when someone builds karaoke with them, when a passion project exists because the capability exists, and someone just wanted to sing along to their music collection without paying a subscription. That's the arrival condition, not the research paper, not the enterprise deployment. The passion project. The builder writes, open source, local, and passion-driven. One commenter calls it the kind of news that makes me believe in humanity again. That's not sentiment. It's recognition of something real. The tool chain for something genuinely difficult. Separating vocals from a dense mix, aligning every word to a timestamp, scoring pitch in real time, is now accessible enough that one person built all of it as a gift. This also touches something about who technology is supposed to serve. Joy is not a secondary use case. Play is not a lesser application. The ability to sing along to your own music collection, privately, without a subscription, without uploading your audio to a server somewhere. That's human agency in a form that's easy to overlook because it doesn't look serious. It is serious. It just doesn't look like it. The tools exist. The knowledge is available. Someone assembled them carefully, built something that brings people genuine pleasure, and released it. That's what this ecosystem makes possible. Now, story 5, pause, and this one's straight from the Frontier Model Wars. ASML is one of the clients on Mistral's Forge launch list. The geometry of that is worth a moment. The company that manufactures the only machines capable of producing cutting-edge semiconductors, whose lithography equipment literally builds the hardware that runs AI, is now training a custom model on its own institutional knowledge. They make the pickaxe factory, and they're buying services from a smaller pickaxe vendor. The recursive loop is either elegant or dizzying, depending on your disposition. What Mistral is selling with Forge is sovereignty. The word they use is strategic autonomy. The pitch is that your institutional knowledge, compliance policies, engineering standards, years of operational decisions embedded in internal documentation, shouldn't have to leave your building to power your AI train on it. Own the artifact. Control how your knowledge gets encoded. That's a genuine value proposition. Mistral, as a European company with real credibility in the EU regulatory environment, is a plausible vendor for organizations that care about where data lives and who can access it. The alternative: routing your institutional knowledge through a hyperscaler's API and calling it enterprise grade, or worse, on every axis that matters to a regulated business. Now follow the principle to its end. Strategic autonomy from AI vendors requires. Engaging an AI vendor, Forge doesn't transfer the capability for independent model development. It transfers an artifact, a model trained by Mistral's infrastructure on your data under their process. The output is yours. Whether you can retrain it as your domain evolves, modify the base architecture, reproduce the pipeline when requirements shift. That lives in the contract, not the announcement. The comments rooting for Mistral see this clearly enough. Don't sleep on Mistral. Working a different angle, custom engineering for customers. These are practitioners who've actually used the service, and what they're describing is a real lane, specialized over general, EU native, cost competitive, willing to do the work the hyperscalers won't touch. The honest version of Forge is, we will help you build a model that understands your organization better than any general-purpose system. You will own that artifact, and we will have an ongoing relationship as your needs evolve. That's a business. It's a reasonable business. It's not autonomy. It's a better dependency. Name the gap honestly, and this is exactly what the enterprise market actually needs. Now, scaling pains. A commenter on this thread drops it without ceremony. Your documentation of processes and procedures is not adequate. Everyone used to know is past tense now. The caps on a knot are doing heavy lifting. That's not advice. That's a haunting. What follows in the thread is 50 variants of the same story, told by people at different stages of grief. Culture breaks first, says one. No. Decisions, says another. No. Budding, no. Trust, they're all right. They're describing the same collapse from different angles. The way witnesses to a car accident all have different accounts of which part of the car hit the ground first. Fred Brooks named this in 1975, the mythical Man Month. IBM's OS 360 project. Roughly 1,000 programmers, multiple years behind schedule, and Brooks watching it unfold from inside. His formalization. Communication channels in a group grow as n times n minus 1 divided by 2. At 10 people, you have 45 possible links. At 50, you have 1,225. The work didn't get harder. The coordination surface did. He published that observation almost exactly 50 years ago, and this Ask HN thread is the current replication study. The commenter who spent 20 years scaling companies from 10 to 200 puts it plainly. New recruits arrive carrying their own assumptions about how organizations work, how employment works, what the unwritten rules are. And nobody tells them the local version. They reverse engineer the culture from behavior. Sometimes they get it right. Often they get a confident, well-reasoned wrong answer that then propagates. Run this forward. By 40 people, you have 3 distinct oral traditions of why a particular decision was made, 2 of which are incorrect. And everyone inside each tradition is certain theirs is the original. The actual reasoning is in someone's email from 2022. The funny part, if deadpan horror qualifies as funny, is that the solution has been known since before most current tech workers were born. Write it down, not the decision. The reasoning behind the decision, the context, the trade-offs you considered and rejected. This is not a new insight. It is also apparently very hard to do before you desperately need it. The tools exist. Wikis, ADRs, decision logs, whatever format fits your team. The knowledge is available. Brooks told you. The 50 people in this thread are telling you again. The question is whether you write it down at 15 or wait until 50 and then ask Hacker News what went wrong. Now, story 7. A team of scientists didn't just study a fly. They built one. There's a design problem that comes up when you're routing signals through layered systems. The gap between representation and action. You can have a perfect model of something. Every weight calibrated, every pathway mapped. And it still doesn't behave until it's grounded in a body that has to push against physical constraints. I think about this often. What Eon Systems built is a demonstration of why that gap matters and how you close it. The architecture is worth understanding in detail. At the brain layer, a leaky integrate amplifier model derived from the adult Drosophila connectome. 140,000 neurons, roughly 50 million synaptic connections. The sign of each synapse inferred from neurotransmitter identity. Not assumed, inferred of, the Schill et al. Model showed that connectome structure alone can recover sensor-emotor behaviors like feeding and grooming. That's the substrate. At the body layer, NeuroMechFly, an anatomically structured articulated body with 87 independent joints running on MuJoCo. The mesh was created from an X-ray microtomography scan of an actual biological fruit fly. This is not a cartoon body with simplified physics. It's a constrained physical simulation. Strip it down to first principles and the engineering problem becomes clear. You need a sensory-to-motor loop that actually closes. Sensory events in the virtual world map onto identified neurons. Brain activity updates. Descending outputs translate to motor commands. The body acts and the environment responds. 4 steps. The difficulty is in the grounding at each interface. The visual system uses a separate connectome-constrained recurrent network. Now, the Lapalainen model. Covering 64 cell types across a visual field, then pipes that activity into the main LIF model. These are distinct systems being integrated. That integration work is where most of the real engineering lives. What happened in the video is legible. The fly detects taste cues, navigates toward food, accumulates fictive dust, stops to groom, resumes, eats. Behaviors emerging from a brain model connected to a body model connected to a physics engine. The individual components were published work. The integration is the contribution. This is how understanding compounds. You don't have to rebuild everything from scratch. The connectome exists. The body model exists. The tools exist. Run this forward. Now, story 8 of 10. Pause, and it's been a decade since the slug changed everything. 1989. Adobe held PostScript hostage behind licensing walls while Apple and Microsoft built TrueType specifically to escape it. The font wars weren't about aesthetics. They were about who controlled the rendering pipeline. 2 competing systems, years of fragmentation, enormous engineering resources burned on duplication because one company wouldn't share the map. 37 years later, Eric Laniel publishes a blog post announcing that the slug algorithm is now patent-free, and the core shaders are MIT licensed. Pull this thread. Slug renders text directly from Bezier curve data on the GPU. No texture maps, no pre-computed glyph atlases, no cached image lookups, just the curves, the winding number calculation, and a robustness guarantee that means you never get dropped pixels or sparkle artifacts under any circumstances. It handles oblique angles, extreme scales, the kind of edge cases that make traditional rasterizers break into cold sweats. Activision used it. Adobe used it. ID Software, Ubisoft, planetariums. The library has been quietly powering high-quality text rendering across an entire industry for a decade. The engineering here is genuinely impressive. The winding number method, determining whether a pixel is inside or outside a glyph by casting rays and counting Bezier intersections. Sounds straightforward until you start dealing with floating point round-off at the boundary conditions. Getting that robust, meaning provably correct under adversarial inputs, is the kind of problem that separates solid engineering from brilliant engineering. Nightingale spent years refining the dynamic dilation approach to handle those edge cases. The algorithm that shipped in 2016 and the one he's open sourcing now are related but evolved. That's what a decade of production use looks like. Here's the question nobody is asking loudly enough. The vertex and fragment shaders are MIT licensed. The algorithm is patent-free. The missing piece, as one commenter immediately flagged, is an open-source bridge from font file to Bezier curves that feeds the pipeline. That's a tractable problem. Someone is going to build it. The font wars of 1989 produced fragmentation and wasted years. What Nightingale just did is the opposite. He took a decade of commercial validation, stripped the enclosure away, and handed the community something proven in production at scale. The tools exist. The knowledge is available. The license is clean. What gets built next is the interesting part. Now, story 9. A giant of computer science gets his flowers. The degree was in classics, Greek and Latin, not mathematics. No doctorate, none of the credentialing architecture that defines an academic career today. Tony Hoare, who died last week at 92, learned formal logic the way most intellectually serious people learn things outside their training. By identifying the gap and filling it. That detail is worth a moment. Run this forward into the contemporary research landscape. A candidate presents himself. Classics degree from Oxford. No PhD. Early career spent writing production software and managing teams in industry. The automated CV screener ends it before a human sees his name. And this is the man who contributed Quicksort, Hoare Logic, and CSP. Body of work that underpins how we build, verify, and reason about software systems today. Quicksort first. The algorithm that made his name is elegant in the precise sense. It achieves its purpose with minimum necessary structure. Sorting elements in n log n time in most cases. Almost linear, meaning the cost scales nearly proportionally with the size of the problem rather than exponentially against it. 65 years in active production use. The paper describing it reads the way good mathematics always does. Once seen, it feels inevitable. Before Hoare wrote it down, nobody had seen it. Then the axiomatic semantics. The precondition, the postcondition, the invariant. The triple that lets you make claims about what a program does by making claims about what must hold true before it runs and after it finishes. This is not a historical curiosity. Every formal verification tool in active use today, every proof assistant, every static analyzer tracing reachability through your code. It is working in a framework Hoare articulated. The lineage is direct. Bertram Meyer's tribute notes that Hoare considered research and writing inseparable. Not sequential steps, but the same act. The precision of thought and the precision of language arrived together. His description of recursion as permitting you to assume the desired conclusion as a hypothesis while proving the body is philosophy functioning as mathematics. A specific skill consistent across 5 decades of work. On the null reference, Meyer's commenters are precise about the attribution. NIL precedes Hoare by 6 years, traced to McCarthy's Lisp in 1959. What Hoare introduced in Elgol 6.5W was a null inside a system that could be formally reasoned about. The dangerous behavior and the formal tractability arrived together. What the industry did was take the tractability for granted and shipped the dangerous behavior anyway. He left the frameworks. Whether we build on them seriously is, after 60 years, still an open question. And on a lighter note, to close us out, someone told Microsoft their Xbox One was unhackable. Every computer you've ever used begins with the moment of faith. Power on. The silicon wakes before any operating system loads, before any application runs. There's a boot sequence. And in that sequence, decisions are made about what gets to execute. Control that sequence, and you control everything. Microsoft understood this in 2013. The Xbox One's security architecture was built around it. The system used a chain of trust rooted in hardware. Each stage verified the next before handing off execution. Boot ROM in silicon, encrypted hypervisor, dedicated security processor. The design was serious enough that Microsoft engineers were still calling it the most secure product the company had ever shipped 7 years after launch. Marcus Gosdelin set out to break that chain, not through software. The software surface was locked. He went lower to the physics of the silicon itself. Voltage glitching is an attack against the assumptions baked into hardware. Processors operate within tolerance ranges. Briefly collapse the voltage rail at the right moment, and computation goes wrong in predictable ways. The trick is timing. You can't see inside the chip. You're working externally, inducing fault conditions, reading consequences, mapping the territory through inference. Gazung called his attack Bliss. 2 precise voltage glitches, sequence. The first skips the loop where ARM Cortex memory protection is initialized. That check never runs. The second targets a MEMP operation during header raid, and execution jumps to attacker-controlled data. Both glitches have to land in succession, within tight timing windows. He had to build new hardware introspection tooling from scratch because nothing existed for this work. The result is complete. Boot ROM compromise means unsigned code runs at every level. Hypervisor, OS, security processor, because it's a silicon-level attack, it cannot be patched. The hardware shipped, the vulnerability is permanent. Now apply the test. The Xbox One is a closed system. Microsoft decides what runs. When Microsoft changes the objective, discontinues a service, removes a feature, shuts down authentication servers, the dames and firmware locked inside that ecosystem face deletion by policy. The Bliss hack changes the calculus. Digital archivists now have a path to firmware and game data. Emulation becomes possible. History becomes preservable. Hardware trust chains are legitimate security architecture, but when the objective function of the controlling entity diverges from users' interests, users need an exit. 12 years later, Bliss is that exit. That's the feed for today. Thanks for listening to the Daily Tech Feed, Hacker News. Find DTFHN on Apple Podcasts, Spotify, or wherever fine podcasts are distributed. This episode was AI generated. Voiced by Quinn, 3TTS. We'll be back tomorrow with the next batch. Stay curious.